A frozen moon orbiting far beyond Earth should be dead, silent, ancient, unchanging. And yet, one tiny world near Saturn is doing something impossible. It is spraying vast plumes of water into space from beneath an icy shell hundreds of millions of years old. Deep below its frozen surface, something is generating heat movement, and perhaps even the conditions for life itself. What NASA found on Enceladus did not merely challenge planetary science. It forced us to ask a far more unsettling question. Are we truly alone? So, before you settle into the story, take a moment to like the video and subscribe if you enjoy exploring the mysteries of the universe, and tell us your location and local time in the comments below. Now, let's begin. Out near the frozen edge of the giant world. Saturn, beyond the warmth of Earth, beyond the familiar brightness of the inner planets, there is a tiny moon so bright it almost looks unreal. It reflects sunlight like fresh snow under a winter sun, glowing with a cold brilliance against the darkness of space. If you had looked at it through a telescope 200 years ago, you would have seen almost nothing remarkable. Just a small white dot orbiting a ringed giant. Silent, frozen, easy to ignore. And for a very long time, that is exactly what humanity did. In 1789, the astronomer William Herschel discovered this moon while studying Saturn. Herschel was already famous for discovering the planet Uranus, expanding the known boundaries of the solar system for the first time in modern history. But this new discovery did not generate the same excitement. Saturn already had moons. Another one especially, a tiny one, did not feel revolutionary. It was catalogued, measured, named, and quietly filed into astronomy's growing archive of celestial objects. The moon would later be called Enceladus, named after a giant from Greek mythology, a powerful being buried beneath the earth, whose movements caused earthquakes and eruptions. At the time, the name felt poetic. In hindsight, it feels almost prophetic. From Earth, Enceladus offered few clues about its true nature. It is small, astonishingly small by planetary standards, only about 500 kilometers across. If you placed it over the continental United States, it would barely cover a few states. It is less than 1/7 the diameter of Earth's moon. In cosmic terms, it is tiny. And small worlds are not supposed to stay active for long. That assumption came from a simple truth about heat. Imagine taking a hot loaf of bread from an oven. A large loaf stays warm for a long time because its interior traps heat. A small bread roll cools much faster because heat escapes easily from its surface. Worlds in space behave similarly. Large planets like Earth can hold internal heat for billions of years. Small moons should lose that heat relatively quickly, becoming geologically dead. No volcanoes, no tectonics, no internal movement, just frozen silence. Enceladus seemed like the perfect example of such a dead world. And it had another problem. Distance. Saturn orbits nearly 10 times farther from the Sun than Earth does. Sunlight out there is weak, pale, and almost powerless. By the time solar energy reaches Saturn, it has thinned, dramatically spread across enormous distances until it provides only a tiny fraction of the warmth Earth receives. If Earth's sunlight feels like standing near a campfire, Saturn's sunlight feels like seeing that same fire from miles away. You know it exists, but you feel almost nothing. That means Enceladus lives in extraordinary cold. Its surface temperature averages around -200 degrees Celsius. At those temperatures, water ice becomes harder than granite. Snow there does not crunch underfoot. Ice there behaves like rock. If you could stand on Enceladus, the cold would not simply feel uncomfortable. It would feel hostile to chemistry itself. Molecular motion slows. Reactions stall. Energy vanishes. Everything about this world should scream one conclusion. Nothing happens here. And yet, one detail made Enceladus quietly strange. Brightness. Enceladus reflects nearly 90% of the sunlight that reaches it, making it one of the most reflective objects in the entire solar system. That is an astonishing number. Fresh snow on Earth reflects a great deal of sunlight, but Enceladus exceeds even that. Its surface is so white, so pristine, that it almost looks polished. That alone raised a subtle question. Space is messy. Over time, dust, radiation micrometeor impacts, and solar particles darken surfaces. Ancient worlds usually look weathered, scarred, dirty, old. So why did Enceladus look so clean? At first, nobody treated that question as urgent. Astronomy in the 19th and early 20th centuries had larger mysteries to solve. New planets, nebulae stars, galaxies, relativity, quantum mechanics. Compared with those revolutions, a small moon near Saturn barely mattered. Enceladus remained in the background, a name in textbooks rather than a frontier of discovery. But science has a habit of rewarding patience. Sometimes the biggest discoveries hide in the smallest places. By the late 20th century, humanity's tools had changed. Telescopes improved. Detectors became more sensitive. Most importantly, we stopped observing distant worlds only from Earth. We began sending machines into the deep. Space probes transformed astronomy from distant observation into direct exploration. For the first time, humans could approach alien worlds close enough to see landscapes, craters, mountains, fractures, and weather. The solar system stopped being abstract points of light and became a collection of real places. And Enceladus was about to go from irrelevant to extraordinary. When the Voyager program spacecraft launched in the late 1970s, their mission was ambitious beyond precedent. They would cross the outer solar system, visiting giant planets and their moons, collecting data that no telescope on Earth could ever capture. Their cameras would show humanity the true faces of worlds never seen up close. For Enceladus, this would be the first real test. Would it confirm everything scientists expected? A dead, ice-covered moon, ancient and silent? Or would it reveal something else? As Voyager approached, Saturn, anticipation grew. Dozens of moons orbited the ringed giant. Most were expected to be frozen relics, leftovers from the solar system's violent formation. Enceladus ranked low on the list of priorities. Few expected it to matter. But sometimes discovery begins not with something spectacular. Sometimes it begins with something that does not make sense. A surface detail, a pattern break, a contradiction, something small enough to overlook, something large enough to change everything. When Voyager finally sent back close images of Enceladus, scientists noticed something impossible. The moon's surface did not behave like the surface of a dead world should. Part of it looked ancient, battered by impacts over immense spans of time. But another part looked strangely smooth, almost young, as if something had erased history itself. That observation raised a question no one had anticipated. What could possibly be reshaping a frozen moon this small in the deep cold beyond Saturn? And that question would become the beginning of one of the most astonishing investigations in planetary science. Because Enceladus was not dead. It had simply been waiting for us to look closer. When the first close images of Enceladus arrived from the Voyager program missions in 1980 and 1981, scientists expected confirmation of an old assumption. They expected to see a small frozen moon covered in craters from billions of years of impacts. That is, after all, what dead worlds usually look like. In space-time, leaves scars. Every asteroid strike becomes a permanent record unless something actively erases it. On worlds without weather, oceans, or geology craters are history written in stone. The older the surface, the more scars it carries. At first glance, Enceladus appeared to fit that pattern. There were craters, lots of them. Some were enormous, stretching more than 30 kilometers across. Their circular rims stood like frozen wounds across the icy crust, evidence of ancient collisions dating back to the violent early solar system, when rocks and ice constantly slammed into young planets and moons. To planetary scientists, crater counts are more than surface features. They function almost like tree rings. Count enough impact scars and you can estimate age. More craters usually mean older terrain. Fewer craters suggest something has resurfaced the landscape more recently. This technique had worked across the solar system. It helped scientists reconstruct the history of Mars, Earth's moon, and the icy moons of the outer planets. It was reliable, elegant, powerful, and then Enceladus broke the pattern. The strange thing was not that Enceladus had craters. The strange thing was where those craters stopped. Voyager's images revealed a startling contrast. The northern hemisphere looked ancient, heavily cratered, and geologically quiet. But as scientists examined regions farther south, something strange began happening. The large craters became fewer, then smaller, then rarer still. Eventually, entire regions appeared astonishingly smooth, almost spotless. It was as if half the moon had aged normally, while the other half had somehow been renewed. That made no sense. Imagine flying over a desert where one side is filled with weathered ruins thousands of years old, while the other side looks as though the land had been freshly paved yesterday. Same environment, same exposure, completely different ages. Instantly, you would know something unusual had happened. That was exactly the problem with Enceladus. There is no cosmic rule saying asteroids strike only one hemisphere. Space debris does not selectively avoid the South Pole. Impacts should distribute relatively evenly over geological timescales. So, if craters were missing, one conclusion became unavoidable. Something had erased them. That realization changed everything. Suddenly, the question was no longer whether Enceladus was interesting. The question became much more unsettling. What force was resurfacing this moon? Scientists began listing possibilities. Could micrometeor dust be slowly filling in craters over time? Unlikely. The process would be far too slow and too uniform to explain such dramatic regional differences. Could tectonic activity crack and reshape the crust, perhaps? But small moons were not supposed to sustain internal tectonics for billions of years. Could ancient impacts have melted large sections of the surface possible, but that still failed to explain how smooth some areas remained? Every explanation created new problems, and the more researchers examined the data, the stranger Enceladus became. Some smooth plains looked almost young on geological timescales, not millions of years younger. In some cases, potentially hundreds of millions or less. That might sound ancient by human standards, but in solar system terms, it is remarkably recent. If those regions truly had been resurfaced, then whatever caused it happened long after Enceladus should have cooled into permanent dormancy. That was the contradiction. Enceladus was too small to stay warm, too cold to stay active, too old to still be changing, and yet the surface was telling scientists something else. Something inside this moon had moved. The implications reached beyond geology. Internal activity requires energy. Energy requires a source. And sources of internal energy on icy worlds are rare. A large rocky planet may retain primordial heat from formation. Radioactive decay can contribute heat over time. But Enceladus was tiny. Tiny worlds cool fast. That fundamental physical rule had shaped decades of planetary science. If Enceladus truly remained active, then either scientists were missing an important heat source, or their understanding of icy moons was incomplete. That possibility was uncomfortable. Science advances through anomaly, but anomalies are disruptive. They force experts to question frameworks they trust. Most of the time, anomalies disappear with better data. Measurement errors, instrument noise, misinterpretations. But sometimes anomalies survive, and when they do, they become gateways to discovery. Enceladus was beginning to look like one of those gateways. Then another mystery entered the story, not on the moon itself, but around Saturn. Astronomers had long known that Saturn possessed not only its famous bright rings, but also a faint outer ring almost invisible to casual observation. This diffuse structure, called the E-ring, was enormous. Vast clouds of tiny icy particle spread far beyond Saturn's main rings, forming a ghostly halo around the planet. Unlike the bright, dense rings, the E-ring was faint and diffuse, almost like cosmic fog, and its existence posed a puzzle. Particles in rings do not last forever. They collide, break apart, drift, fall inward, escape outward. Over long timescales, rings need replenishment, or they disappear. That means if Saturn's E-ring still existed, something had to be feeding it continuously. Something nearby, something icy, something active. And as scientists mapped the orbits of Saturn's moons, one fact stood out with unnerving precision. Enceladus orbited directly through the densest region of the E-ring. That coincidence was difficult to ignore. It was almost too perfect. Could Enceladus somehow be supplying material to Saturn's ring? At first, the idea sounded absurd. How could a tiny frozen moon eject enough ice into space to maintain a planetary ring? That would require constant mass loss, continuous release of particles, a mechanism powerful enough to throw material beyond the moon's weak gravity and into orbit around Saturn. A dead moon could not do that. Only an active world could. Now, two separate mysteries were beginning to overlap. Mystery 1. Why was Enceladus missing craters in the south? Mystery 2. What was feeding Saturn's E-ring? And slowly, a disturbing possibility emerged. What if these were not two mysteries at all? What if they were symptoms of the same hidden process? What if something inside Enceladus was reshaping its surface, while also launching material into space? That idea sounded extraordinary. But extraordinary ideas demand extraordinary evidence. Voyager had raised the questions. It could not answer them. The spacecraft flew past Saturn only briefly. Their mission continued outward into deeper space, leaving behind more questions than answers. Scientists now had hints, patterns, contradictions, but not proof. The mystery remained unsolved. For years, Enceladus returned to silence. A small moon, a strange surface, an unresolved anomaly. But hidden inside one old Voyager photograph was a clue no one noticed at the time. A clue so subtle it would remain overlooked for years. And once scientists finally saw it, Enceladus would stop being merely strange. It would become astonishing. Far beyond the visible beauty of Saturn's famous rings lies something far stranger. If you could drift outward through the bright icy bands that dominate every textbook image, you would eventually enter a region so faint that your eyes might miss it entirely. There, surrounding the giant planet like an enormous ghostly halo, exists Saturn's E-ring. It is not dense like the main rings. It does not shine with dramatic brilliance. Instead, it hangs in space like frozen mist, a vast cloud of microscopic ice grains spread across hundreds of thousands of kilometers. Quiet, delicate, almost invisible. And yet, this faint ring was hiding one of the most important clues in the Enceladus mystery. At first, the E-ring seemed like a minor curiosity. It was discovered through sensitive observations that revealed light scattering from incredibly tiny particles. These grains were mostly ice reflecting faint blue-white light. But once astronomers began studying the ring more carefully, a troubling question emerged. Rings are not stable forever. Space may appear empty, but it is never truly still. Tiny particles constantly collide, fracture drift, and gradually disperse. Over time, sunlight, electromagnetic forces, and gravitational interactions disturb delicate structures. Left alone, long enough, a diffuse ring like the E-ring should fade away. But Saturn's E-ring had not vanished. It was still there. That meant something had to be replenishing it, continuously. Imagine seeing steam rising from a cup of tea. If the steam keeps rising hour after hour, you immediately know something must still be heating the water. Steam without heat makes no sense. In the same way, a ring filled with fresh ice grains implied an active source. Somewhere in Saturn's system, something was constantly injecting new material into space. So scientists began asking a simple question. Where was the source? They mapped the orbital paths of Saturn's moons. They compared distances, trajectories, and ring density distributions. And one result stood out so clearly it almost felt suspicious. Enceladus orbited directly through the densest region of the E-ring, not near it, not adjacent to it, right through its thickest concentration. That coincidence immediately attracted attention. Could Enceladus be feeding the ring? At first, scientists proposed conservative explanations. Perhaps tiny meteoroids constantly bombarded Enceladus's surface, blasting ice dust into orbit like powder kicked from dry snow. Over millions of impacts, enough material might escape the moon's weak gravity to replenish the ring. The theory sounded plausible until researchers ran the numbers. The math was discouraging. Random impacts simply could not generate enough material at the necessary rate. The E-ring contained too many particles too consistently distributed for passive erosion alone to explain it. Something more energetic seemed necessary. Something active. That possibility created a startling implication. If Enceladus truly supplied Saturn's E-ring, then the moon had to be losing material in massive quantities. Not occasionally, not during rare catastrophic events, continuously. And that raised a disturbing question. How could a frozen moon eject material into space on an ongoing basis? There are only a few ways for worlds to launch matter beyond their gravity. Violent impacts can do it. Volcanic eruptions can do it. Powerful internal pressure can do it. But every serious mechanism implied energy, heat, internal motion, everything Enceladus was not supposed to have. The contradictions were stacking higher. Scientists revisited Voyager imagery, examining old data with fresh eyes. This is one of science's strangest truths. Sometimes, discoveries are not made by gathering new information, but by asking better questions of old information. Data can sit quietly for years until someone recognizes what matters. That is exactly what happened. Buried in one of Voyager's old photographs was something subtle. So subtle that it escaped attention during the original mission analysis. The image showed Enceladus against the dark backdrop near Saturn. At first glance, nothing seemed unusual, but when researchers processed the image more carefully, they noticed something odd. A faint extension, a distortion, almost like a tail. Not a solid tail like a comet, but a diffuse elongation of brightness trailing away from the moon. It was barely visible, almost dismissible as imaging noise. But once noticed, it became difficult to ignore. Why would a moon appear to have a tail? That single question transformed interpretation. If material was escaping from Enceladus, even in tiny amounts, sunlight scattering through those particles might create exactly such a visual signature. The possibility was electrifying. Voyager may have captured evidence of escaping material decades earlier, without anyone realizing it. Suddenly, the resurfaced southern hemisphere and Saturn's mysterious ring no longer felt like separate puzzles. They began aligning into a single narrative. Imagine a hidden underground spring beneath a frozen lake. Water under pressure forces its way upward through cracks in the ice. Some water freezes on the surface, smoothing old scars. Some escapes into the air, forming mist. One process creates two visible effects. Could Enceladus work the same way? Could material erupt from beneath the surface, fall back to erase craters, and simultaneously escape into orbit to feed the E-ring? The idea was extraordinary, but it still suffered from a major problem. No one had actually seen an eruption. There were no visible geysers, no direct proof, only circumstantial evidence. And in science, circumstantial evidence can inspire hypotheses, but it cannot settle them. The field reached an uncomfortable pause. Enceladus had become deeply suspicious. But suspicion is not confirmation. Researchers now needed something far more valuable than theory. They needed a closer look, a much closer look. That meant returning to Saturn with better instruments, more sophisticated sensors, and a mission designed not merely for flyby snapshots, but for long-term investigation. Humanity needed a spacecraft that could orbit Saturn for years, repeatedly observing its moons from multiple angles, measuring heat chemistry, gravity, and structure with unprecedented precision. In other words, Enceladus needed a detective, and that detective was already being built. In 1997, a spacecraft carrying some of the most advanced scientific instruments ever sent into deep space began a journey that would last nearly 7 years. It was a collaboration between NASA, European Space Agency, and Italian Space Agency. Its name would become legendary, Cassini Huygens mission, and when Cassini finally reached Saturn, the mystery of Enceladus would stop being theoretical, because Cassini was about to see something no human had ever imagined. Not just ice, not just craters, but signs of something alive beneath the surface. In October 1997, a rocket rose from Earth carrying one of the most ambitious scientific missions ever attempted. Its destination was not the Moon, not Mars, but the outer solar system, nearly 1.5 billion kilometers away. The spacecraft aboard that rocket had a single purpose: to reveal the hidden secrets of Saturn and its moons. It would travel for almost 7 years, slingshot around planets to gain speed, survive deep space radiation, and carry instruments precise enough to detect invisible gases, tiny dust grains, faint thermal emissions, and subtle gravitational shifts. This mission was humanity's most sophisticated attempt yet to understand Saturn's system. Its name was Cassini Huygens mission. By the time Cassini launched, Enceladus had already become a scientific oddity. Researchers knew 3 unsettling facts. First half, its surface looked geologically young. Second, something appeared to be feeding Saturn's E-ring. Third, those 2 mysteries might be connected. But might is a dangerous word in science. It signals possibility, not proof. Cassini's job was to replace speculation with evidence, and Cassini was built for exactly that. Unlike the Voyager probes, which sped past Saturn during brief encounters, Cassini would enter orbit around Saturn and stay there for years. That changed everything. Imagine trying to understand a city by flying over it once in an airplane. You might notice landmarks, rivers, roads, but you would miss daily life. You would miss patterns. You would miss change over time. Cassini was not a flyover. It was a long-term investigation. It would watch Saturn's system breathe. Its instrument suite was extraordinary. High-resolution cameras, infrared spectrometers, ultraviolet detectors, magnetometers, dust analyzers, gravity science tools. Each instrument was like a different sense. One could see heat. Another could identify molecules. Another could detect particles too small for cameras. Another could measure invisible magnetic disturbances. Together, they transformed Cassini into something more than a camera. It became a floating laboratory. On July 1st, 2004, Cassini performed one of the most critical maneuvers in planetary exploration history. It fired its main engine and slipped into orbit around Saturn. Humanity had arrived. For the first time, scientists could study the ringed planet not as a distant object, but as a dynamic system of interacting worlds. Giant storms churned through Saturn's atmosphere. Rings rippled with gravitational waves. Moons carved gaps and resonances through icy particles. It was breathtaking. But among all these wonders, one tiny moon kept pulling attention: Enceladus. At first, even Cassini's mission planners did not fully understand how important this moon would become. Saturn has over 100 moons and moonlets. Several were already considered major targets. Titan, Saturn's largest moon, attracted enormous scientific interest because of its thick atmosphere and methane lakes. Enceladus, by comparison, was small and easy to underestimate. But science does not reward assumptions. It rewards anomalies. And within Cassini's earliest observations, Enceladus began violating expectations again. The first close images revealed a surface even stranger than Voyager had suggested. The smooth regions were not merely smooth. They looked fresh. Sharp-edged fractures cut across icy plains. Ridges twisted across the surface like frozen tectonic scars. In some regions, crater counts were astonishingly low, implying surfaces far younger than expected. Not ancient relics, young terrain. Young meant recent activity. Recent activity meant ongoing energy. That alone was unsettling. But then Cassini saw something near the South Pole that stopped scientists cold. 4 enormous fractures. Parallel, deep, unmistakable. They stretched across the South Polar region like claw marks across glass. Long blue-tinted scars carved into the ice. These fractures were unlike anything previously seen on Enceladus. They were so distinctive that scientists gave them a memorable name. Tiger stripes. The name sounded almost casual. The discovery was anything but. Each stripe extended for more than 100 kilometers. Together, they formed a bizarre geological pattern no simple impact could explain. These were not crater rims. They were structural fractures, evidence of enormous stress acting within the moon's crust. And there was something even stranger. Color. The ice within and around these fractures looked unusually bright and chemically distinct. Fresh. Cleaner than surrounding terrain. In planetary geology, bright, clean ice often means young surface exposure. Old surfaces darken from radiation and micrometeor contamination. Fresh ice suggests recent resurfacing. That meant the tiger stripes were not ancient scars preserved in frozen time. They were active regions. But active in what way? Cracks alone were not enough to prove internal heat. Frozen ice can fracture under stress without requiring liquid water beneath it. Scientists needed stronger evidence. Cassini had a way to get it. Infrared imaging. If visible cameras show what a surface looks like, infrared instruments reveal something far more important: temperature. They detect heat radiation invisible to human ears. Even slight temperature differences become measurable. When Cassini aimed its infrared sensors at Enceladus's south pole, the results stunned mission scientists. The tiger stripes were warm, not warm by human standards, warm relative to Enceladus. That distinction mattered. The moon's average surface temperature hovered around minus 200 degrees Celsius. It should be uniformly brutal. But the tiger stripes were dramatically hotter than surrounding terrain, reaching roughly minus 128 degrees Celsius in places, still lethally cold, but impossibly warm for a supposedly dead moon. This was the turning point. A smooth surface could perhaps be explained by ancient resurfacing. A strange fracture pattern might perhaps result from long frozen tectonic stress. But active heat emission happening right now, that changed the conversation completely. Something inside Enceladus was generating energy in the present, not millions of years ago, now. This realization spread rapidly through the planetary science community. The old model of Enceladus as a frozen relic was collapsing. Every new measurement pushed the same conclusion. This moon was active. The question was no longer whether Enceladus was geologically alive. The question became much more urgent. What was powering it? Heat must come from somewhere. Energy cannot appear from nothing. Something beneath that ice shell was feeding these fractures. Something powerful enough to warm entire regions against the crushing cold of the outer solar system. Scientists began considering possibilities. Residual heat from formation. Unlikely after billions of years. Radioactive decay. insufficient for such localized anomalies. Tidal heating from gravitational stress. Possible, but the numbers were not yet convincing. Then mission planners proposed a clever experiment. They would not just photograph Enceladus. They would use light itself as a probe. A distant star would soon pass behind Enceladus from Cassini's perspective. If the moon had no gas around it, the star's light would vanish sharply the moment the solid body blocked it. But if gas surrounded the moon, even faint gas, the light would dim gradually before disappearing. It was a simple idea, elegant, powerful, and it would answer a question nobody had dared ask directly. Did Enceladus have an atmosphere? The answer when it came would be even more shocking than the tiger stripes, because Cassini was about to detect something impossible above the South Pole. Not just heat, not just fractures, but water escaping into space. The experiment sounded almost too simple to uncover something revolutionary. Cassini would watch a distant star as Enceladus passed in front of it. If nothing surrounded the moon, the starlight would remain steady until the exact moment Enceladus blocked it. Sharp, instant, like switching off a lamp. But if gas existed above the surface, even an extremely thin layer, the light would begin fading before the moon fully crossed the star. That fading would act like a fingerprint, revealing the presence of an atmosphere. No one expected much. After all, atmospheres require gravity or constant replenishment. Large worlds like Earth can hold thick envelopes of gas because gravity continuously pulls molecules inward. Small worlds struggle. Molecules escape into space. Over time, atmospheres leak away. And Enceladus barely had gravity at all. If you stood on its surface, gravity would feel almost non-existent. A person weighing 70 kilograms on Earth would effectively weigh only a few kilograms there. Jump too hard, and you might travel alarmingly high. Escape velocity was so low that retaining gas over long timescales should have been nearly impossible. That was the assumption. Cassini challenged it. As the observation began, instruments locked onto the star. Data streamed back across nearly 1.5 billion kilometers of space. Scientists monitored brightness curves in real time, waiting for the clean drop expected from a bare, icy moon. But that is not what happened. 24 seconds before the star disappeared behind Enceladus, Cassini's ultraviolet spectrometer detected something strange. The starlight dimmed. Gradually, subtly, but unmistakably, gas was there. Not only gas, water vapor. That moment transformed Enceladus again. It had an atmosphere. A weak one? Yes. Extremely tenuous by Earth standards. You could not breathe it. You would barely even notice it. But scientifically, its existence was astonishing. This tiny moon frozen in the deep outer solar system somehow possessed gaseous water suspended above its surface. That alone raised immediate questions. Where did the vapor come from? And more importantly, how was it being replenished? Because a thin atmosphere around Enceladus could not survive long without a constant source. Molecules would escape quickly into space or fall back to the surface. Maintaining atmospheric water vapor required active supply. Something was feeding it, continuously. Then, Cassini delivered an even more disturbing result. Scientists compared measurements from different regions of the moon. The atmosphere was not uniform. It was strongest near the South Pole. That detail changed everything. If the gas had come from slow sublimation, where surface ice gradually turns into vapor under sunlight, the atmosphere should have been more evenly distributed. But it wasn't. The concentration dramatically increased near one specific region, the South Polar terrain, the same region containing the tiger stripes. Now, multiple independent lines of evidence were converging. Young terrain, missing craters, thermal anomalies, atmospheric water vapor, all pointing to one place, the South Pole. At this stage, planetary scientists were no longer dealing with isolated anomalies. They were looking at a coherent pattern. And coherent patterns in science are dangerous in the best possible way. They force a shift in worldview. Imagine hearing faint tapping inside a wall. One tap means nothing. Two taps may still be coincidence, but repeated tapping from the same location tells you something is inside. Enceladus was tapping, loudly. Something beneath the South Pole was active. But what? Scientists proposed increasingly bold hypotheses. One idea suggested subsurface reservoirs of liquid water under pressure. Cracks in the ice could act like pressure valves releasing vapor into space. Another possibility involved sublimation chambers where buried ice heated enough to flash directly into vapor. Others suggested tectonic flexing repeatedly opening and closing fractures, pumping material upward. Each hypothesis attempted to explain one critical fact: the atmosphere was localized. Localized activity implies localized energy, and localized energy implies structure beneath the surface. Cassini's mission team needed direct visual evidence, not indirect measurements, not spectral inference. They needed to actually see the source. That opportunity arrived during another carefully planned observation. This time, Cassini positioned itself so the sun sat behind Enceladus. The geometry was perfect. Under normal illumination, faint particles near the surface are difficult to see because reflected surface light overwhelms them. But with the sun behind the moon, forward scattered light from tiny particles becomes dramatically visible. It is similar to driving through fog at the sunset. Sometimes the fog seems invisible until light hits it from just the right angle. Suddenly, every suspended droplet glows. Cassini would use that same principle. The images came in. At first, scientists saw the moon's familiar bright edge. Then something appeared. Faint streaks. Vertical, rising from the South Pole. At first, they seemed like imaging artifacts. Stray light, sensor noise. But frame after frame showed the same structures. Bright streams extended outward from the tiger stripe region into space. They were real, not haze, not noise. Plumes, massive plumes, gigantic columns of gas and ice erupting from the surface. Everything changed in that moment. The atmosphere was not passive. It was being created in real time. Enceladus was venting material into space, violently, continuously, and not in tiny amounts. The plumes extended hundreds of kilometers above the surface. Millions of tons of material were escaping. The scale was staggering. What had once been a quiet moon now resembled a pressurized world, venting its interior into space. Scientists stared at the images with disbelief, because they were no longer looking at a dead icy moon. They were looking at active geology, real ongoing geological activity, in the outer solar system, on a moon only 500 kilometers wide. That should not have been possible. And yet, there it was, visible, undeniable. But the images raised an even deeper mystery. What exactly was erupting? Water vapor explained the atmosphere. Ice particles explained the E-ring. But what mechanism could generate eruptions powerful enough to launch material beyond Enceladus's gravity? Ordinary cracking was not enough. Surface fractures alone were not enough. Pressure had to build somewhere below, which meant the most radical possibility was becoming harder to avoid. There might be liquid water under the ice, not frozen slush, not isolated pockets, real liquid water. And if liquid water existed beneath that shell, then Enceladus was no longer merely geologically active. It was something far more extraordinary. Potentially habitable, but extraordinary claims demand extraordinary evidence. Seeing plumes was revolutionary. Understanding what was inside them would be even more important. There was only one way to know. Cassini would have to do something unprecedented. It would have to fly directly through the eruptions, straight through the plume itself. By now, NASA had crossed a scientific threshold. Enceladus was no longer merely a strange moon with unexplained geology. It had become something much more provocative, a world actively ejecting material from its interior into space. The South Pole was venting gigantic plumes of water vapor and ice particles hundreds of kilometers above the surface, feeding Saturn's vast E-ring while continuously reshaping its own terrain. The evidence was overwhelming. But one essential mystery remained unsolved. Scientists still did not know what those plumes actually contained. And until they knew that they could not understand what was happening beneath the ice. Photographs could reveal structure. Thermal maps could reveal heat. Spectroscopy could identify broad molecular signatures. But there is a limit to what distant observation can tell you. Eventually, if you want real answers, you need to collect samples. That requirement created a problem. Cassini was never originally designed to study Enceladus as a primary mission target. Its trajectory had been planned years earlier, long before anyone suspected this tiny moon might hide one of the solar system's greatest mysteries. No one had designed a special lander. No cryobot. No drilling system. No probe capable of descending beneath the ice. And yet, Enceladus offered something no other ocean world had ever offered. It was already ejecting material for us. Think about how extraordinary that is. On worlds like Europa, if scientists want to search for subsurface oceans, they may one day need to drill through kilometers of solid ice. That could require enormous engineering challenges, decades of development, and staggering cost. But Enceladus was doing something almost unbelievable. It was spraying samples of its interior directly into space, as if the moon itself were handing us pieces of its hidden ocean. All we had to do was catch them. That realization changed mission planning overnight. Cassini's team proposed a daring maneuver. They would alter the spacecraft's trajectory and send it directly through the plume columns erupting from the south polar fractures. Not nearby. Not observational distance. Through them. This was risky. Cassini was moving at enormous speed relative to Enceladus several kilometers per second. At such velocities, even microscopic particles can become dangerous. A tiny grain of ice traveling at high relative speed can strike with the energy of a bullet. Flying through a dense particle field is not trivial. Too many impacts could damage instruments or worse, but the scientific reward was too great. Mission planners accepted the risk. Cassini would become humanity's first spacecraft to sample material directly from a potentially habitable alien ocean. The flyby began. As Cassini descended toward the moon, Enceladus grew larger in its cameras. The brilliant white sphere filled more of the frame. The tiger stripes came into view, dark scars slicing through the south polar terrain. Somewhere below those fractures, pressure was building. Water, vapor, ice, chemistry, energy. Then the spacecraft entered the plume. At that moment, Cassini's onboard instruments switched into collection mode. One of the most important tools was its cosmic dust analyzer, designed to capture and analyze microscopic particles in space. Another instrument, the ion and neutral mass spectrometer, could identify gases and molecules by measuring mass and charge. Together, they acted like forensic investigators at a crime scene. They began reading the plume, and the first result confirmed what scientists had strongly suspected. Water. A tremendous amount of water. The plume was overwhelmingly composed of water vapor and ice grains. That alone was historic, but water by itself was only the beginning. Water tells you something important about physical state, but not necessarily about habitability. The real question was more profound. Was the water chemically interesting? Cassini continued collecting. Then came the first major surprise. Salt. The plume particles contained sodium salts. That detail might sound small, almost mundane. After all, salt is common on Earth. We put it on food. We dissolve it in water. We barely think about it. But in planetary science, salt can be explosive evidence. Why? Because salt usually implies prolonged interaction between liquid water and rock. Imagine rainwater flowing through underground stone for years, dissolving minerals along the way. The water gradually becomes chemically enriched. Rivers carry those dissolved minerals to oceans, giving seawater its saltiness. The same logic applies elsewhere in the solar system. Salt in Enceladus's plume suggested something profound. This was not just melted surface ice. This water had touched rock. That implication sent shockwaves through the scientific community. Because if liquid water was interacting with a rocky core, then Enceladus might possess not merely isolated melt pockets near the surface, but a deep internal water system, potentially an ocean. The evidence kept coming. Cassini detected carbon-bearing compounds, methane, carbon dioxide, simple organics, then more, nitrogen compounds, hydrogen-bearing molecules. The chemical picture was becoming increasingly complex. This was no sterile jet of pure frozen water. The plume carried chemistry, rich chemistry, and chemistry matters, because life, as we understand it, is chemistry organized into astonishing complexity. At the most basic level, life on Earth depends on several essential ingredients: liquid water, carbon chemistry, usable energy, and stable environmental conditions, allowing molecules to interact long enough to build complexity. Remove one of those ingredients, and biology becomes difficult or impossible. Cassini was beginning to check those boxes. Water, yes. Carbon chemistry, yes. But scientists remained cautious. Ingredients do not equal life. A kitchen full of flour, eggs, and sugar is not automatically a cake. Ingredients matter, but what matters even more is the process that transforms them. That process requires energy. And Enceladus posed a serious problem. Where was the energy coming from? This question became impossible to ignore. Water requires heat to remain liquid. Pressure can help salts can lower freezing points, but at Saturn's distance from the Sun and surface, heating is essentially irrelevant. The energy source had to be internal. Something inside Enceladus was generating enough heat to maintain liquid water, pressurize it, and drive eruptions powerful enough to blast material into space. That required enormous sustained energy. More than anyone expected, Cassini's plume data did something subtle but critical. It changed the scientific question. Earlier researchers were asking whether liquid water might exist somewhere beneath the South Pole. After the fly-through, that question became outdated. Now the question was bigger. How extensive was that water? Was it just a localized reservoir under the tiger stripes, or something much larger? To answer that, scientists turned away from chemistry and back toward physics, specifically motion, because Enceladus was doing something strange in its orbit around Saturn. Something subtle, something almost invisible. A tiny wobble, a slight rocking motion, small enough to overlook, powerful enough to reveal what lay beneath the ice. And once scientists measured that wobble precisely, the hidden truth of Enceladus would become impossible to deny. Because the moon was not hiding a lake, it might be hiding an entire ocean. At first, the movement seemed insignificant, a tiny oscillation, a slight rocking motion in the way Enceladus rotated as it orbited Saturn. To most people, it would look meaningless. But in planetary science, tiny motions often reveal enormous truths. Sometimes a world tells you what lies inside not through what you can see on the surface, but through how it moves under gravity. To understand why, imagine holding a raw egg and a hard-boiled egg. From the outside, they look almost identical. Same size, same shell, same shape. But if you spin them, the difference becomes obvious. The hard-boiled egg spins smoothly because its interior is solid. The raw egg wobbles because liquid inside continues moving independently from the shell. That is the key. Internal structure changes motion, and Enceladus was wobbling. This wobble is called libration. The word sounds technical, but the idea is surprisingly intuitive. Like Earth's moon, Enceladus is tidally locked, meaning the same side always faces Saturn. If you lived on Saturn and looked at Enceladus in the sky, you would always see the same hemisphere. But tidal locking does not mean perfect stillness. Because the orbit is not a perfect circle, Small variations in gravitational pull cause the moon to rock slightly back and forth. That rocking can be measured, and Cassini measured it. The numbers initially seemed subtle. The wobble was tiny, fractions of degrees. But when scientists modeled how a fully solid Enceladus should behave, something did not fit. The wobble was too large, much too large. A completely solid icy moon should resist that degree of libration. Its outer shell and core would rotate as one rigid body limiting motion. But Enceladus behaved differently, as though the outer ice shell could move somewhat independently of the interior. That implied separation. Something had to decouple the shell from the core. Something fluid. This is where the entire Enceladus story changed. Before Cassini, scientists entertained modest possibilities. Perhaps a few melt pockets beneath the South Pole? Maybe regional reservoirs of water. Localized heating around the tiger stripes? Interesting, yes, but limited. Libration shattered that comfortable model, because the simplest explanation for the measured wobble was astonishing. A global subsurface ocean. Not a lake, not a cavity. An ocean wrapped around nearly the entire moon, trapped beneath kilometers of ice. That conclusion felt almost absurd. A tiny frozen moon, only 500 kilometers across, orbiting in near total darkness, containing an entire ocean beneath its surface. And yet the evidence kept pointing there. Scientists began combining multiple datasets. Gravity measurements from Cassini flybys provided mass distribution estimates. Surface deformation patterns offered clues about crust flexibility. Thermal models examined heat transport from the interior. Each independent approach converged toward the same unsettling picture. Beneath Enceladus's frozen shell lay liquid water, lots of it. To appreciate the scale, imagine Earth's Arctic Ocean sealed beneath an ice shell dozens of kilometers thick. No sunlight, no open water, no waves touching air. Just darkness pressure and liquid water surrounding a rocky core. That begins to resemble what scientists now believed existed inside Enceladus. But oceans create new problems. Water does not stay liquid in deep space without energy. Liquid water at Saturn's distance is unnatural. Frozen is natural. Liquid requires explanation. This became the central mystery. What kept the ocean warm? Cassini's data suggested the ice shell thickness varied dramatically. In some regions, especially near the South Pole, the shell appeared much thinner than elsewhere. That matched the plume activity. Thin ice allows heat to escape more easily. Fractures can reach deeper. Pressure can build. Still, even a thin shell should freeze over time unless heat constantly replenishes the system. And freezing should happen fast on geological timescales, unless energy input remained continuous. That forced scientists back to a familiar but unresolved question. Where was the heat coming from? Residual heat from formation seemed inadequate. Enceladus formed billions of years ago. Small bodies cool rapidly. Radioactive decay contributed some energy, but nowhere near enough to sustain a global ocean and drive active plumes. So the heat had to come from something external, not the sun, not internal radioactivity. Something else, something mechanical, something gravitational. To understand that possibility, scientists examined Enceladus's orbit more carefully. And there they found another crucial clue. Enceladus was not orbiting Saturn alone. It danced in a gravitational relationship with another moon, Dione. This relationship is called orbital resonance. Every time Dione completed one orbit around Saturn, Enceladus completed almost exactly two. That repeated alignment mattered because regular gravitational encounters create predictable disturbances. Each time the moons aligned, Dione's gravity tugged on Enceladus. Not enough to dramatically alter its orbit, enough to prevent orbital perfection. Instead of traveling in a perfect circle around Saturn, Enceladus followed a slightly elliptical path. That tiny deviation changed everything. Because elliptical orbits create changing gravitational stress. When Enceladus moved closer to Saturn, gravity pulled harder. When it moved further away, gravity weakened slightly, over and over, closer, farther, pull, release, stretch, relax, again and again. Imagine bending a paperclip back and forth repeatedly. At first, nothing dramatic happens, but continue long enough and friction builds heat in the metal. Eventually, it becomes warm to the touch. That warmth comes from mechanical energy being converted into thermal energy. Scientists began wondering, could Saturn be doing something similar to Enceladus? Could gravity itself be heating the moon? The idea was elegant and terrifyingly powerful, because if Saturn's gravity was repeatedly flexing Enceladus, then the moon was not merely orbiting a giant planet. It was being kneaded by it, constantly, slowly, relentlessly, and deep inside that kneading friction could generate heat. Enough heat perhaps to keep an ocean alive beneath the ice. Enough heat to drive plumes. Enough heat to power chemistry. Enough heat for something even more profound. Because once scientists understood the likely source of Enceladus's ocean, a new question emerged. Not about water, not about ice, about life. Because water alone is not enough. Life needs energy, and Saturn's gravitational grip might be providing exactly that. The question was no longer whether Enceladus had an ocean. The question was becoming far more extraordinary. Could that hidden ocean actually support living systems? Life, at its most fundamental level, is an energy problem. You can have water. You can have carbon. You can have all the chemical ingredients needed to build proteins, membranes, and genetic molecules. But without a steady energy source, chemistry stalls. Molecules drift. Reactions slow. Complexity collapses. Life does not merely require ingredients. It requires a system that keeps chemistry moving far from equilibrium. That is what made Enceladus so puzzling. By now, the evidence for liquid water was becoming difficult to dismiss. Cassini had sampled water-rich plumes. It had detected salts and organics. It had measured a wobble consistent with a global subsurface ocean. But all of that led to a brutal question. How could such a tiny frozen moon possibly sustain enough energy to keep an ocean liquid for billions of years? That question forced scientists to think not like geologists, but like physicists. Energy cannot appear from nowhere. If Enceladus was warm inside, something had to be continuously feeding that warmth. The answer, it turned out, was hidden in gravity. We often imagine gravity as a force that simply pulls objects together, but gravity can do far more than that. Under the right conditions, gravity can bend, stretch, squeeze, and deform entire worlds. And when solid bodies repeatedly deform, friction converts motion into heat. This process is called tidal heating. The easiest way to understand it is with your own hands. Take a rubber ball and squeeze it repeatedly. Each time you compress and release it, the internal material flexes. Continue long enough and the ball begins to warm. That warmth is energy from deformation. Now scale that up. Replace your hand with the gravity of Saturn. Replace the rubber ball with an icy moon. And repeat that squeezing forever. That is Enceladus. Because of its orbital resonance with Dione, Enceladus cannot settle into a perfectly circular orbit. Its path remains slightly elliptical. That tiny imperfection is critical. When Enceladus moves closer to Saturn, the planet's gravitational pull becomes stronger. When it moves farther away, the pull weakens. The change is subtle, but relentless. Closer, stronger pull. Farther, weaker pull. Again and again, billions of times. Each orbit bends the moon ever so slightly. Each bend creates internal friction. Each friction event releases heat. By itself, one flex is insignificant. Over geological time, it becomes an invisible furnace. This was the first model that truly explained Enceladus's internal energy budget. Saturn was not merely hosting Enceladus in orbit. Saturn was actively powering it. That realization changed how scientists saw icy moons altogether. Before this, many small outer moons were considered passive frozen relics. Tidal heating shattered that assumption. A moon does not need to be large to stay active. Under the right gravitational conditions, even a tiny world can remain geologically alive. Enceladus became the perfect example. But there was still a problem. Even the most optimistic tidal heating models struggled to explain the full amount of energy Cassini observed. The tiger stripes emitted enormous heat. Too much, in fact. Some estimates suggested the south polar terrain was radiating several gigawatts of power. That is comparable to the output of multiple large power plants operating continuously. For a moon this small, that was extraordinary. So scientists refined the models further. Perhaps tidal heating was not distributed evenly. Perhaps certain internal structures concentrated stress. Imagine bending a metal ruler. It does not flex equally across every point. Some regions experience greater stress than others. Weak points bend more. Heat concentrates around fractures. Enceladus likely behaved the same way. Its icy shell may contain weak zones near the South Pole. Fractures like the tiger stripes could repeatedly open and close under tidal stress, acting almost like mechanical valves. Every orbit, Saturn's gravity flexes the moon. The fractures widen slightly, pressure rises, water vapor escapes. Then the fractures relax. A cosmic breathing cycle. Inhale, exhale, open, close. The moon was not dead. It was pulsing. That image stunned researchers because it made Enceladus feel strangely alive, not biologically, but dynamically. It behaved like a system exchanging energy with its environment, continuously transforming gravitational motion into thermal activity, and heat changes chemistry. That mattered enormously, because warmth alone is useful. Warmth plus water is transformative. Warmth plus water plus rock becomes something even more interesting. Reactive chemistry. Scientists began focusing on the boundary where Enceladus's ocean touched its rocky core. That interface became one of the most important locations in astrobiology. Wherever liquid water interacts with warm rock, chemical reactions accelerate. Minerals dissolve. Molecules exchange ions. New compounds form. On Earth, such environments are often astonishingly rich, especially deep underwater. This comparison led to one of the biggest conceptual shifts in the Enceladus story. For decades, discussions about extraterrestrial life were dominated by sunlight. Habitability usually meant the Goldilocks zone, the orbital distance where a planet receives enough stellar energy for liquid water at the surface. Too hot and water boils away, too cold and it freezes. But Enceladus violated that logic. It was far outside the Sun's traditional habitable zone, and yet it had liquid water. That meant habitability could no longer be defined by sunlight alone. Life might survive using completely different energy systems, systems powered by geology rather than stars. That possibility pointed scientists toward a profound analog here on Earth, a place where life thrives in total darkness, a place where sunlight never reaches, a place where ecosystems are powered not by photosynthesis, but by chemistry. Deep beneath Earth's oceans, along volcanic ridges and hydrothermal vents, entire ecosystems flourish without a single ray of sunlight. Strange organisms cluster around superheated mineral-rich water emerging from the seafloor. Giant tube worms, exotic microbes, chemosynthetic bacteria. These ecosystems survive by harvesting chemical energy, not solar energy. That discovery revolutionized biology. And now scientists began asking a breathtaking question. If life on Earth can thrive around deep-sea hydrothermal systems in total darkness, could something similar exist inside Enceladus? If the moon's ocean touched warm rock? If tidal heating drove hydrothermal activity? If chemical gradients existed near the core? Then Enceladus might possess not just water and heat. It might possess habitable ecosystems. That possibility would have sounded outrageous only a decade earlier. Now it was becoming scientifically serious. But speculation needed evidence, and evidence was coming. Because hidden within Cassini's plume data were chemical signatures so extraordinary that they hinted at something happening at the bottom of Enceladus's ocean, something startlingly similar to Earth's hydrothermal vents. And once scientists recognized those signatures, the case for habitability would become stronger than anyone imagined. For most of human history, life and sunlight were inseparable. Every forest, every ocean bloom, every animal migration, every breath of oxygen in Earth's atmosphere ultimately traces back to the sun. Even when you eat meat, you are consuming stored solar energy that passed through plants first. Sunlight powers photosynthesis. Photosynthesis powers food webs. Food webs power ecosystems. The chain seems absolute. That assumption shaped early astrobiology. If you wanted to search for life beyond Earth, you looked for places warmed by starlight. That logic was so deeply embedded in science that it almost felt unquestionable. Then, Earth revealed something astonishing. In the late 20th century, oceanographers descended into one of the most hostile environments on our planet, deep below the Pacific Ocean, beyond the reach of sunlight, beyond the familiar world of photosynthesis. They found something impossible. Life. Not sparse life. Abundant life. Thriving life. Entire ecosystems clustered around hydrothermal vents, fractures in Earth's seafloor where superheated mineral-rich water erupted from deep underground. These vents looked almost alien. Towering black chimneys rose from the seafloor, spewing dark mineral plumes into freezing water. Temperatures near the vent openings could exceed 350 degrees Celsius, yet just meters away the surrounding ocean remained near freezing. It was a world of violent contrasts: heat and cold, darkness and chemistry, pressure beyond imagination, and somehow life flourished there. That discovery shattered one of biology's oldest assumptions. Life did not need sunlight. It needed energy, and energy can come from chemistry. Microbes near hydrothermal vents survive through chemosynthesis, using chemical reactions instead of photosynthesis to generate usable energy. Rather than harvesting photons, they harvest chemical disequilibrium differences in molecular energy between compounds. Hydrogen, methane, sulfur, compounds minerals, these become fuel. In other words, where chemistry remains active, life may find opportunity. That realization transformed the Enceladus investigation, because suddenly scientists were no longer asking only whether Enceladus had liquid water. They were asking whether it had the right kind of chemistry, and hidden in Cassini's plume data, the answer began emerging. When Cassini flew repeatedly through the plumes of Enceladus, instruments captured increasingly detailed chemical fingerprints. At first, scientists focused on obvious compounds, water vapor salts, simple carbon molecules. But deeper analysis revealed something more exciting: hydrogen, molecular hydrogen. That detection sent shockwaves through astrobiology, because hydrogen is not just another molecule. Hydrogen can be fuel. On Earth, many microbes use hydrogen in metabolic reactions. Some of the most ancient branches of life likely relied on hydrogen-rich environments near hydrothermal systems. Molecular hydrogen represents stored chemical energy waiting to be exploited. Its presence raised an immediate question: where did the hydrogen come from? Hydrogen can be produced through several pathways, but one explanation stood out as particularly compelling. When warm water reacts with certain types of rock rich in iron and magnesium, chemical reactions can generate hydrogen gas. On Earth, one of the most important of these processes is called serpentinization. The name sounds exotic, but the process is simple in principle. Water penetrates fractured rock deep underground. Minerals react chemically. New minerals form. Hydrogen is released, and that hydrogen becomes potential energy for microbial life. Cassini's hydrogen data suggested something remarkable. Water inside Enceladus was likely interacting directly with warm rock, not merely sitting beneath ice. interacting, reacting, transforming. That implied active geochemistry deep below the surface. Then came another clue: silica particles, tiny grains, easy to overlook, enormously important. Silica forms under specific conditions, especially when hot water interacts with silicate rock at elevated temperatures. On Earth, silica-rich particles are strongly associated with hydrothermal vent systems. Finding silica in Enceladus's plume was like discovering ash drifting from a distant volcano. You may not see the eruption directly, but the particles reveal what happened. This was the moment the Enceladus hypothesis became dramatically stronger. Scientists now had multiple independent indicators pointing towards the same hidden environment: liquid water, rock-water interaction, hydrogen production, silica formation, heat, pressure, chemical gradients. Piece by piece, Enceladus began resembling something hauntingly familiar: a deep ocean world with hydrothermal activity on the seafloor. An alien ocean, powered by geology. The implications were staggering. Imagine descending beneath Enceladus's ice shell. Kilometer after kilometer of frozen darkness surrounds you. No sunlight penetrates, no stars are visible. Eventually, the ice gives way to black water. An enormous hidden ocean stretches in every direction. Far below, near the rocky core, warm mineral-rich fluids seep or erupt from hydrothermal systems. Chemical gradients form, molecules circulate, energy flows. In that darkness, chemistry never stops. And where chemistry never stops, life becomes conceivable. Not guaranteed, but conceivable. That distinction matters. Scientists remained careful. Cassini did not detect life. It detected habitability. That difference is profound. A habitable environment is not the same as an inhabited one. Earth has deserts, glaciers, and acidic lakes that are habitable in principle, yet contain limited life. Conditions alone do not guarantee biology. Life must still originate. And the origin of life remains one of science's deepest unsolved mysteries. How does chemistry become biology? At what threshold does complex molecular organization cross into metabolism, replication, and evolution? We still do not know. That uncertainty kept scientists cautious. Yet something extraordinary had already happened. Enceladus had moved from speculative curiosity to one of the strongest astrobiological targets in the solar system. Not because of imagination, because of evidence. And the evidence was becoming difficult to ignore. By now, researchers often described life as requiring three fundamental ingredients: liquid water, essential chemistry, usable energy. Cassini had provided strong evidence for all three. Water, yes. Chemistry, yes. Energy, yes. That triad changed the conversation permanently. For decades, worlds beyond Earth were categorized largely by size, distance, and surface conditions. But Enceladus introduced a new category entirely: hidden ocean worlds. Worlds whose most important environments lie not on their surfaces, but deep beneath them. That idea expanded the map of habitability across the solar system. Suddenly, moons once dismissed as frozen wastelands became scientifically thrilling. Europa, Titan, even distant icy bodies once considered irrelevant deserved a second look. The habitable zone had grown, not outward from stars, inward beneath ice. But despite all the excitement, one brutal fact remained. No one had found life. Not yet. Cassini had shown that Enceladus could support biology. But could biology actually exist there? Could something be swimming, drifting, metabolizing, evolving in that hidden ocean right now? That question was no longer philosophical. It had become scientific. And to answer it, scientists needed to ask the boldest question yet. If life exists beneath Enceladus's ice, what would it look like? Once you accept that Enceladus may possess liquid water, complex chemistry, and a persistent energy source, a question that once belonged to science fiction suddenly becomes unavoidable. Could something be alive beneath the ice? It is an unsettling question, because it changes the emotional scale of everything you have learned so far. Until now, Enceladus has been a story about geology physics, chemistry, and planetary science. But life changes the stakes. The moment biology enters the conversation, the mystery stops being merely about one moon orbiting Saturn. It becomes a question about us, because if life emerged independently on Enceladus, then life may not be rare. It may be common, and that possibility carries enormous consequences. But before asking whether life exists, their scientists had to ask a more disciplined question. What kind of life could survive in such an environment? The honest answer begins with humility. When humans imagine alien life, we often imagine complexity first. Intelligent beings, large organisms, creatures swimming through dark oceans, strange predators hunting beneath alien ice. But biology on Earth teaches a different lesson. Complex life came late, very late. For most of Earth's history, life was microscopic. Single-celled organisms dominated our planet for billions of years before multicellular organisms appeared. Plants, animals, nervous systems, and intelligence are recent developments. If life emerged on Enceladus, odds strongly favor something simple: microbial life, small, ancient, invisible to the naked eye. But simple can be misleading. Microbes are not primitive in the sense of being weak. Microbial life on Earth survives in places once thought impossible for biology: acidic lakes, boiling hot springs, Antarctic ice, nuclear reactors, deep underground rock, hydrothermal vents, salt crusts, vacuum-like dryness. These organisms are called extremophiles, and they changed biology forever. Extremophiles taught scientists a powerful lesson. Life is far more adaptable than humans once believed. That matters enormously for Enceladus, because conditions beneath its icy shell, while hostile to humans, may not be hostile to all biology. Imagine descending into Enceladus's hidden ocean again. Darkness surrounds you completely. No sunrise ever comes. Pressure increases as you sink deeper. The water is cold overall, but near hydrothermal activity, localized heat creates pockets of energetic chemistry. Mineral-rich fluids rise from fractures in the rocky core. Hydrogen accumulates. Carbon-bearing molecules circulate. Chemical gradients form. To a human, this would feel like an alien abyss. To a microbe, it could feel like opportunity. That distinction is profound. Life does not need comfort. It needs gradients. Wherever energy differences exist, biology may exploit them. On Earth, many microbes do exactly this. Some consume hydrogen and carbon dioxide, producing methane. Others metabolize sulfur compounds. Some survive by exploiting redox chemistry so efficiently that sunlight becomes irrelevant. Scientists began comparing Enceladus's chemistry with Earth's most ancient microbial ecosystems. That comparison led to a fascinating realization. The hidden ocean of Enceladus may resemble environments where life first emerged on Earth. This matters because the origin of life on Earth remains deeply uncertain. We do not know the exact pathway from chemistry to biology, but one leading hypothesis places early life near hydrothermal systems. In these environments, heat mineral surfaces and chemical disequilibrium create natural laboratories for molecular complexity. Think of hydrothermal vents as chemical engines. They continuously push molecules out of equilibrium, creating opportunities for increasingly complex reactions. Without such disequilibrium, chemistry tends to settle into stable states. Complexity fades. But where gradients persist, systems can self-organize. This is where Enceladus becomes so compelling. Its ocean may possess precisely those ingredients: persistent water, reactive minerals, hydrothermal energy, long timescales. That combination is powerful, and time matters more than many people realize. Enceladus is old, very old. It formed billions of years ago, likely not long after Saturn itself. That means if habitable conditions persisted for extended periods, biology, if it began, may have had immense spans of time to evolve. Billions of years. That is difficult to comprehend. Imagine every human civilization ever recorded compressed into a single second. Even then, billions of years stretch far beyond human intuition. Evolution works slowly but relentlessly. Given time, even simple systems can diversify in astonishing ways. That possibility led some researchers to ask increasingly bold questions. Could Enceladus support more than microbes? The cautious scientific answer remains probably not impossible, but highly speculative. Large multicellular organisms require abundant energy. Earth's oceans support complex life partly because photosynthesis generates enormous biomass. Enceladus likely has much lower total energy throughput. Less available energy usually means smaller ecosystems. That makes microbial biospheres the most plausible scenario. Still, even microbial life would be revolutionary. Consider what that would mean. A second Genesis, not descendants of Earth, not contamination, independent life, an entirely separate biological origin. That would mean biology is not a miraculous singular accident confined to one planet. It would mean the universe may naturally produce life whenever conditions allow. And that realization would rewrite science. It would transform biology into cosmic biology. But scientists remained careful for one critical reason. Habitability is not proof. Even with all the evidence, Cassini never detected a biosignature strong enough to confirm living systems. No cellular structures, no unmistakable biological molecules, no direct metabolic markers. The mission revealed possibility, not certainty, and uncertainty is where good science lives. This distinction became so important that in 2017, when the Cassini Huygens mission neared its end, NASA made a dramatic decision. They deliberately destroyed Cassini, not because the spacecraft had failed, because it had succeeded too well. Scientists feared that if Cassini remained uncontrolled long enough, gravitational perturbations might eventually send it crashing into Enceladus or Titan. Even though the spacecraft had been sterilized before launch, absolute sterility is nearly impossible. A few Earth microbes might survive in protected niches, and that created an ethical problem: planetary contamination. If terrestrial microbes reached Enceladus, future life detection missions could become compromised forever. Scientists might discover biology without knowing whether it originated there or came from Earth. That risk was unacceptable. So Cassini was sent into Saturn's atmosphere, where it burned and vaporized. Its final act was one of scientific humility. Protect the worlds we may someday study for life. But Cassini's death created another problem. The best spacecraft ever sent to Saturn was gone, and the most important question remained unanswered. Is Enceladus merely habitable or inhabited? To answer that, humanity would need to return. Not someday in theory, with missions designed specifically to search for life. And those missions may do something Cassini never could. They may look directly for biosignatures inside the plume, or perhaps even bring samples home. Because the next chapter of the Enceladus story will not be about discovery alone. It may be about confirmation. When the Cassini-Huygens mission ended in 2017, humanity lost more than a spacecraft. We lost our eyes at Saturn. For 13 years, Cassini had transformed a distant planetary system into something intimate and real. It gave us storms the size of continents rings, sculpted by gravity methane lakes on Titan, and perhaps most astonishing of all, an icy moon that should have been dead, yet seemed alive with internal motion. Cassini did not merely study Enceladus. It changed what Enceladus meant. Before Cassini, Enceladus was a minor moon. After Cassini, it became one of the most important astrobiological targets in the solar system. And that created a strange frustration, because Cassini had brought us right to the edge of an answer, then stopped. Imagine reading the greatest mystery novel ever written only for the final chapter to be torn out. That is where planetary science suddenly found itself. We had evidence of a global ocean, evidence of hydrothermal activity, evidence of organics, salts, hydrogen, and chemical energy. We had a compelling case for habitability, but not proof of life. The final question remained untouched. Is anything alive there? That question immediately reshaped the future of space exploration. Scientists began designing missions not simply to observe Enceladus, but to interrogate it. Every proposed mission centered on one ultimate goal: detect biosignatures, chemical or structural evidence that biology exists or once existed. But finding life is harder than it sounds. The problem is not only distance, it is ambiguity. Many molecules associated with life can also form through non-biological chemistry. Methane organics and carbon compounds alone are not enough. Even amino acids would not automatically prove biology. Nature can create many building blocks without life. Scientists therefore needed stronger indicators: patterns, complexity, disequilibrium, ratios difficult to explain without metabolism. This is where future missions become far more sophisticated than Cassini. Cassini was never built as a dedicated life detection mission. It carried remarkable instruments, but not the full suite modern astrobiologists would ideally want. Future probes could carry ultra-sensitive mass spectrometers capable of distinguishing molecular structures with far greater precision. They could search for amino acid, chirality, lipid fragments, isotopic fractionation, or repeating molecular distributions suggestive of biological selection. These details may sound technical, but the principle is simple. Life leaves fingerprints, not always obvious fingerprints, but patterns. Repeated biased organized patterns that chemistry alone struggles to explain. And Enceladus may be spraying those fingerprints directly into space. That is what makes this moon uniquely exciting. Unlike most ocean worlds, Enceladus may not require drilling, no tunneling through 20 kilometers of ice, no robotic submarines descending into alien seas. The moon is already doing the excavation for us. Every plume eruption carries samples from the hidden ocean upward through fractures and into space. Each eruption is like a natural elevator transporting subsurface material to altitudes reachable by spacecraft. That creates an extraordinary opportunity. Future missions may simply fly through the plume again, but this time with instruments purpose-built for biology. Several mission concepts have explored exactly that possibility. Some propose repeated close flybys, passing through the densest plume regions at carefully optimized velocities to maximize sample collection while minimizing destructive impact energy. Others propose orbiters dedicated almost entirely to Enceladus rather than Saturn broadly. And then there are the boldest ideas. Sample return. The concept sounds almost unbelievable. Collect material from Enceladus, seal it, return it to Earth, analyze it inside the most advanced laboratories humanity has ever built. That would represent a monumental leap in capability. Earth-based labs vastly outperform anything we can currently launch into space. Instruments weighing tons on Earth must be miniaturized into kilograms for spacecraft. Returning samples would allow orders of magnitude better sensitivity. Imagine what that could reveal: cell-like structures, complex polymers, membrane fragments, metabolic byproducts, perhaps even something no Earth lab has ever seen before, an alien biochemistry. Even contemplating such a discovery forces uncomfortable philosophical questions. What if life on Enceladus uses familiar chemistry but unfamiliar architecture? Would it still use amino acids? Would it use something analogous to DNA? Would it metabolize hydrogen? Would it be microbial mats clinging to hydrothermal minerals? Or would it challenge our very definition of life? Scientists must remain cautious here. We do not yet know enough to assume Earth-like biology. All life we know shares a common ancestry. That creates a profound limitation. Our understanding of biology comes from a sample size of one planet, one biosphere, one origin. That means the first discovery of truly alien life would not merely expand biology, it could force biology to redefine itself. This possibility is why mission design has become increasingly interdisciplinary. Enceladus missions are no longer just engineering challenges. They require planetary scientists, chemists, geologists, microbiologists, data scientists, and philosophers of science. Because detecting life is not just about measuring molecules, it is about interpretation. How much evidence is enough? What threshold justifies extraordinary claims? When can we say with scientific confidence this is life? These questions matter because history teaches caution. Science has repeatedly mistaken unusual chemistry for biology and biology for unusual chemistry. False positives can mislead entire fields. That is why future missions must gather multiple independent lines of evidence before claiming discovery. One biosignature may intrigue, several aligned biosignatures may persuade. Converging evidence transforms speculation into science. And there is another reason urgency is growing. Time. Space missions move slowly. A mission to Saturn can take years to arrive. Designing, funding, building, testing, and launching such missions can consume decades. Decisions made now may shape discoveries 30 years from today. That reality makes Enceladus strangely emotional. Some of the scientists who helped interpret Cassini's earliest data may never see the final answer. They helped open the door. Others will walk through it. That is the nature of deep science. One generation asks the question, another receives the answer. And sometimes the answer changes civilization. Because if a future probe flies through Enceladus's plume and finds unmistakable biosignatures, the implications will be impossible to contain. Headlines would not merely announce a discovery. They would announce a transformation. Humanity would no longer live in a universe where life is known from only one world. We would become the species that discovered a second Genesis. And that possibility leads to the final, most profound chapter of the Enceladus story, because the ultimate importance of Enceladus was never just about a moon. It was about what that moon says about life in the universe. For most of human history, the universe felt silent. You could look into the night sky and feel wonder, but also isolation. Every star suggested possibility, yet possibility is not evidence. Philosophers speculated. Poets imagined. Scientists calculated probabilities. Civilizations told stories about beings beyond Earth. But beneath all of it remained one uncomfortable truth. We had no proof. None. Not a fossil. Not a microbe. Not a cell. Not even a single unambiguous biosignature. As far as confirmed science was concerned, life existed in exactly one place, Earth. That fact shaped humanity more deeply than we often realize. Every biological process ever studied, every ecosystem ever observed, every evolutionary pathway ever reconstructed. Everything came from one lineage, a single tree of life, whether bacteria in volcanic vents, fungi in forests, whales in the ocean, or humans building telescopes. Every organism on Earth shares ancient ancestry, one origin, one biosphere, one experiment. That is why Enceladus matters so profoundly. Because if something is alive beneath that ice, anything at all, then life did not happen only once. It happened at least twice, and the difference between 1 and 2 is not small. It is civilization changing. Imagine this scenario. A future spacecraft reaches Saturn. It performs repeated passes through Enceladus's plume. Its instruments are more sensitive than anything Cassini carried. Sample chambers collect microscopic ice grains and vapor molecules. Mass spectrometers begin analyzing chemistry in real time. At first, everything looks familiar. Water, salts, organics, hydrogen. Then something appears. A pattern, not random chemistry, not expected equilibrium chemistry. A pattern that repeats. Molecular distributions showing clear biological bias. Complex carbon chains arranged with improbable selectivity. Perhaps amino acids with overwhelming chirality, left-handed or right-handed in a way abiotic chemistry rarely produces. Perhaps membrane-like lipid structures. perhaps isotopic signatures showing fractionation consistent with metabolism. One signal may be questioned. Two signals demand scrutiny. Three independent biosignatures aligned. That becomes difficult to dismiss. Then comes the moment every astrobiologist has imagined. The data survives peer review. Replication confirms it. Alternative abiotic explanations fail, and humanity says the words, "Life exists beyond Earth." Pause there, really pause, because those 6 words would divide human history into 2 eras. Before discovery, after discovery, there would be no returning to the old worldview. The psychological shock would be immense, not because alien microbes threaten us, but because they permanently alter our understanding of our place in reality. For centuries, scientific revolutions repeatedly displaced human centrality. Nicholas Copernicus showed Earth is not the center of the cosmos. Charles Darwin showed humanity is not separate from biological evolution. Modern cosmology revealed our galaxy is one among hundreds of billions. Each discovery made us smaller physically, yet deeper intellectually. A second Genesis would continue that pattern. We would no longer be the only known living world. Earth would become one inhabited node in a much larger biological universe. And suddenly a terrifyingly beautiful possibility emerges. If life formed independently on Enceladus, how many other worlds host life? That question changes everything. Because Enceladus is not unique in possessing water. Our solar system alone contains multiple ocean worlds. Europa likely hides a global ocean beneath ice. Titan has complex organic chemistry and subsurface water. Even distant dwarf planets may conceal buried oceans insulated beneath frozen crusts. And beyond our solar system, thousands of exoplanets have already been discovered. Many orbit within habitable zones. Some are likely water-rich worlds. Some may possess subsurface oceans. Some may host entirely unfamiliar chemistries. Enceladus would become more than a discovery. It would become a statistical argument. Because if life emerged independently on a tiny moon orbiting a gas giant in deep cold, then biology may arise wherever physics permits stable chemistry and energy flow. Life may not be rare. It may be what matter naturally does. That possibility is both thrilling and unsettling, because it forces a profound shift in perspective. We often think life is fragile, and in many ways it is. Civilizations collapse. Species go extinct. Worlds freeze or burn. But perhaps life itself is stubborn, persistent, adaptive, a phenomenon that repeatedly emerges wherever the universe creates the right gradients. In that view, biology becomes less like a miracle and more like a natural phase transition, like ice forming in cold water, like stars igniting under gravity. Given the right conditions, life happens. That idea carries enormous philosophical weight. It suggests consciousness may not be an isolated cosmic accident. Perhaps the universe tends toward complexity, toward awareness, toward systems capable of observing themselves. And if so, then Enceladus becomes something strangely poetic. A tiny frozen moon, once ignored, once dismissed, once catalogued as insignificant, may help answer one of the oldest questions humanity has ever asked. Are we alone? Yet science demands restraint. This is where honesty matters most. We have not found life on Enceladus. Not yet. That distinction must remain clear. What we have found is extraordinary evidence of habitability, a global ocean, chemical complexity, hydrothermal signatures, energy gradients, potential biosignature pathways, everything needed for life as we understand it, everything except confirmation. And uncertainty is not failure. Uncertainty is invitation. Science progresses not by certainty alone, but by better questions. Enceladus has given us one of the greatest questions of our age, and perhaps that is its most profound gift. Because sometimes discovery does not begin with answers. It begins with realizing how much larger the question truly is. Once Enceladus looked like a meaningless white dot. Now it feels like a doorway, a frozen shell hiding a dark ocean. That ocean may be empty, or it may contain chemistry moving slowly toward biology. Or perhaps right now, beneath kilometers of ice, microbial ecosystems already metabolize around hydrothermal vents, completely unaware that a species from a distant blue planet has begun searching for them. That image is staggering. Somewhere, under alien ice in absolute darkness, life may already exist, not waiting to be created, only waiting to be discovered. And that leaves us with one final thought. If life can emerge in darkness beneath the frozen crust of a moon nearly 1.5 billion kilometers from the sun, then perhaps life is not the exception. Perhaps life is the rule, which means the real mystery may no longer be whether life exists elsewhere. The real mystery may be this: how many living oceans are still waiting in the dark? By now, the question facing scientists was no longer simply whether Enceladus could support life. That question had largely been answered. Yes, at least in principle. Liquid water appeared to exist beneath the ice. Chemical building blocks were present. Internal energy sources seemed strong enough to drive complex chemistry. Hydrothermal activity was increasingly plausible. Enceladus had crossed a threshold few worlds ever reach. It was habitable, but habitability is only the beginning. The next challenge is much harder. How do you detect life when you cannot see it? That sounds like a technical problem, but it is really a philosophical one, because life is not a single molecule. There is no universal life particle that instruments can simply search for. Life reveals itself indirectly through patterns that chemistry alone struggles to produce. Scientists call these patterns biosignatures. A biosignature is not life itself. It is evidence that life may have been there. The challenge is separating biological fingerprints from clever non-biological chemistry. And that is far more difficult than most people realize. Imagine walking into a forest and seeing footprints in mud. You do not see the animal. But the tracks tell you something moved through that space. Size-shape spacing patterns reveal agency. Biosignatures work similarly. Scientists search for molecular footprints. But what kind of footprints would alien life leave in Enceladus's plume? One powerful candidate is molecular chirality. This may sound abstract, but the concept is beautifully simple. Hold up your left hand. Now hold up your right. They are mirror images. Same components, same fingers, same structure. But they are not interchangeable. You cannot perfectly overlay one onto the other. Molecules can behave the same way. Some organic molecules exist in left-handed and right-handed versions. Chemically, both can form through non-biological processes. But here is the fascinating part: life often shows preference. Life chooses. On Earth, amino acids used in proteins are overwhelmingly left-handed. Sugars used in biology are overwhelmingly right-handed. That preference is not random. Biology introduces bias, and bias is detectable. If a future mission finds strong molecular handedness in Enceladus's plume, scientists would become extremely interested. Random chemistry tends toward balance. Biology often breaks symmetry. That makes chirality a potential fingerprint of life. Then there are isotopes. At first glance, isotopes seem obscure, but they are another powerful clue. Atoms of the same element can contain slightly different numbers of neutrons, making some versions heavier than others. Carbon, for example, has multiple isotopic forms. Life often prefers lighter isotopes. Why? Because lighter isotopes generally require slightly less energy in biochemical reactions. Over time, living systems subtly reshape isotopic ratios. This creates measurable bias. Imagine sorting coins by weight. If someone consistently selects lighter coins from a mixed pile, the remaining pile changes composition. Biology does something similar with atoms. That means unusual isotope ratios can hint at metabolism, not proof, but a clue. Then, scientists search for something even more intriguing: chemical disequilibrium. This concept lies at the heart of life. Life maintains imbalance. That may sound strange because we usually associate balance with stability. But biology survives by resisting equilibrium. a dead system settles. A living system continuously moves energy matter and information to stay organized. Your body does this right now. Cells constantly consume energy to maintain structure. Stop energy flow and equilibrium returns. Life ends. The same principle applies at planetary scales. If Enceladus's plume contains combinations of molecules that should quickly react away but somehow remain abundant, that suggests continuous replenishment. Something may be maintaining disequilibrium. Possibly geology, possibly biology. Scientists must distinguish between them. That distinction is everything. Because the greatest danger in life detection is false confidence. History repeatedly teaches caution. Researchers have announced possible life before, only to later discover abiotic explanations. Exciting claims can collapse under better data. That is why no serious scientist wants a single dramatic signal. They want convergence, multiple independent biosignatures, all pointing towards the same conclusion. Only then does confidence rise. And Enceladus introduces another complication. What if alien life does not resemble Earth life at all? This possibility is deeply unsettling. All biology we know shares common ancestry. Even bacteria and humans use the same basic molecular language. DNA, RNA, proteins, amino acids, lipid membranes. That shared architecture shapes how we search for life. But what if Enceladus hosts a second genesis, an entirely independent origin? Then its biochemistry might overlap with Earth's, or it might diverge radically. Perhaps it uses familiar carbon chemistry. Perhaps not. Perhaps it uses amino acids. Perhaps different polymers. Perhaps its membranes behave differently. Perhaps its metabolism exploits chemical pathways Earth never evolved. This is where life detection becomes profoundly difficult. We risk searching for life we already understand, and missing life that does not fit our expectations. That danger forces scientists to widen the search, instead of asking only, what molecules indicate Earth-like biology? They increasingly ask, what patterns indicate organized complexity? That subtle shift matters enormously, because life may not announce itself through familiar molecules. It may reveal itself through structure, through improbability, through organization that chemistry alone struggles to explain. And if such patterns are hiding inside Enceladus's plume, then every eruption may already be carrying biological evidence into space, waiting, suspended inside microscopic ice grains, riding invisible columns hundreds of kilometers above the surface, waiting for instruments precise enough to recognize what they contain. That realization brings us to an extraordinary possibility. The next mission to Enceladus may not merely improve our data. It may answer the oldest scientific question humanity has ever asked. Because, for the first time in history, we are building missions designed not to search for habitable worlds, but to search directly for life itself. And those missions may soon return to Saturn, with one purpose: find the answer. Some discoveries arrive by accident. Others require deliberate pursuit. Everything humanity learned about Enceladus up to this point came from a mission that was never designed to search for alien life. That fact is easy to overlook, but it makes the story even more extraordinary. The Cassini Huygens mission did not launch with Enceladus as its central objective. It was built to study the broader Saturn system. And yet, almost by accident, it found one of the strongest candidates for extraterrestrial habitability ever discovered. That raises a thrilling question. What happens when we stop studying Enceladus incidentally and start targeting it deliberately? That is the next chapter of exploration, and it may become one of the most important scientific missions humanity has ever attempted. The challenge begins with distance. Saturn lies nearly 1.5 billion kilometers from Earth. Even traveling at extraordinary speeds, missions to Saturn require years just to arrive. That means every design decision matters. Instruments cannot be swapped later. Mistakes cannot be easily corrected. A mission launched today may not return its most important results for 15 years or more. In other words, when we go back to Enceladus, we need to go prepared. Scientists have proposed several mission architectures. The simplest is a dedicated plume fly-through orbiter. This idea builds directly on Cassini's success. Instead of merely passing through the plume a few times, a specialized spacecraft could perform repeated targeted fly-throughs with optimized trajectories. Its instruments would be designed specifically for life detection. Ultra-high-resolution mass spectrometers, advanced particle capture systems, isotope analyzers, microfluidic biochemical labs. Think of it as upgrading from binoculars to a microscope. Cassini told us the plume contains chemistry. A dedicated orbiter could tell us whether that chemistry carries biological signatures. Repeated sampling would matter enormously. One fly-through can be misleading. Multiple passes across different plume densities, different fracture regions, and different eruption phases would build statistical confidence. Scientists could compare temporal changes, molecular distributions, and plume variability. Patterns would emerge, and patterns reveal truth. But some researchers want to go further, much further. Instead of analyzing samples in space, why not bring them home? This is the concept of sample return. At first, it sounds almost impossible. Collect microscopic material from an erupting alien plume, preserve it, prevent contamination, transport it across billions of kilometers, return safely to Earth. And yet, technically, it may be achievable. The reward would be enormous. Earth-based laboratories are incomparably more powerful than spacecraft instruments. Even our best space hardware faces brutal limits in size, power, mass, radiation tolerance, and computational capability. Laboratories on Earth do not suffer those constraints. A sample return mission would allow scientists to perform thousands of analyses impossible in deep space. Electron microscopy, nanoscale imaging, ultra-sensitive chromatography, high-precision isotopic analysis, single-particle structural reconstruction, potential biomolecular sequencing if recognizable polymers exist. This possibility is intoxicating because it creates a breathtaking scenario. A tiny sealed capsule lands on Earth. Inside it are microscopic grains of ice from a hidden ocean beneath alien ice. That sample may contain nothing extraordinary, or it may contain evidence that changes civilization forever. But some scientists argue even sample return is not enough. They want to go deeper, literally. They envision one of the most ambitious robotic missions ever conceived, a cryobot, a machine designed to melt through Enceladus's ice shell. The concept feels like science fiction. A nuclear-powered probe lands on the surface near the South Pole. Slowly, it melts downward through kilometers of ice, transmitting data upward through fiber optic tether or relay systems. Eventually, after years of descent, it reaches the hidden ocean. Then comes the next step, deployment of a submersible, an autonomous robotic explorer entering an alien ocean for the first time in human history. Imagine that moment. Darkness in every direction. No sunlight, no horizon, only black water illuminated by artificial lights. Then the vehicle descends toward the rocky seafloor. Sensors detect heat, mineral plumes, hydrothermal activity, and perhaps something moving. That vision captures public imagination for obvious reasons. But the engineering challenge is staggering. Ice thickness may exceed tens of kilometers. Extreme pressure sterilization requirements, communication delay, energy supply, contamination control. Every variable becomes brutally difficult. Such a mission remains far beyond current practical deployment. Still impossible today does not mean impossible forever. History repeatedly reminds us of this. Landing on Earth's moon once sounded absurd. Sending rovers to Mars once sounded unrealistic. Flying helicopters on Mars once sounded ridiculous. Tomorrow's impossible often becomes routine science. That is why Enceladus excites engineers as much as scientists, because the problem is not merely scientific, it is civilizational. Can humanity build tools capable of answering its oldest question? That question becomes more urgent for another reason: planetary protection. If Enceladus truly hosts habitable environments, or even life, future missions must avoid contamination at extraordinary levels. One careless microbial hitchhiker from Earth could compromise decades of science. Imagine spending billions of dollars to detect life only to discover the signal came from contamination introduced by your own spacecraft. That nightmare shapes every mission discussion. Sterility becomes sacred. We are no longer merely exploring dead rocks. We may be approaching living worlds. And that changes the ethics of exploration. For the first time, humanity must seriously ask, what responsibilities do we have toward extraterrestrial ecosystems? Do we preserve them untouched, study them remotely, sample cautiously? These are not abstract philosophical questions anymore. Enceladus made them real. Because if something lives beneath that ice, it may have evolved independently for billions of years, isolated from Earth since the birth of the solar system. An entire biosphere, untouched, unaware, ancient beyond imagination, and perhaps closer to discovery than ever before. The next mission to Enceladus may not simply refine Cassini's data. It may do something unprecedented in human history. It may cross the threshold from possibility to proof. And if that happens, the consequences will extend far beyond science. They will reach philosophy, religion, culture, civilization itself. Because confirming life on Enceladus would not merely answer a scientific question. It would force humanity to redefine what it means to be alive in the universe. There are discoveries that expand knowledge. Then there are discoveries that redefine reality. Finding life beneath the ice of Enceladus would belong to the second category. It is difficult to overstate how profoundly such a discovery would affect humanity because its impact would extend far beyond laboratories, scientific journals, or space agencies. This would not be just another headline about a new planet, a new moon, or a new chemical signature. It would strike something far deeper. It would change the story we tell about ourselves. For thousands of years, humans have looked into the night sky and asked the same question in different forms. Are we alone? Ancient civilization asked it through mythology. Philosophers asked it through reason. Religious traditions framed it through theology. Scientists reframed it through observation and probability. But despite all our progress, despite radio telescopes, interplanetary probes, and space observatories, the answer has remained painfully incomplete. We do not know. That uncertainty has shaped civilization in subtle ways. It influences how we define life, intelligence, meaning, and even destiny. As long as Earth remains the only known living world, humanity occupies a strange position in the universe. We are both ordinary matter and something astonishingly rare, atoms formed in stars, molecules assembled on a young planet. Chemistry crossed an invisible threshold into biology. Biology evolved toward complexity, consciousness, memory, language, and technology. Eventually, matter became capable of studying itself. That journey already feels extraordinary. But if life exists on Enceladus, then something fundamental changes. Earth stops being unique, not special in the sense of beauty or significance, but no longer singular. That distinction matters, because there is a vast difference between a universe where life happened once and a universe where life happened multiple times independently. The first suggests rarity. The second suggests inevitability. That difference changes probability across cosmic scales. Imagine flipping a coin and getting heads once. Interesting. Flip a coin twice and get heads both times. Still possible. But if life emerges independently on two worlds within one solar system, Earth and Enceladus, the statistical implications become enormous. Because our solar system is tiny compared to the galaxy. The Milky Way contains hundreds of billions of stars. Many of those stars have planets. Many of those planets likely have moons. Some moons likely contain oceans. Some oceans likely possess chemistry and energy. And if biology naturally emerges under such conditions, then the galaxy may not be silent. It may be full, not necessarily full of civilizations, not necessarily full of intelligence, but full of biology, microbial worlds, ocean worlds, hidden ecosystems, living chemistry unfolding in darkness. That possibility reshapes one of science's most famous puzzles. The Fermi paradox asks a haunting question. If intelligent life is common, where is everyone? Enceladus suggests a partial answer. Perhaps life is common, but intelligence is not. Perhaps the universe overflows with microbial oceans, subsurface biospheres, and primitive ecosystems that never evolve radio telescopes, cities, or civilizations. Perhaps biology frequently begins but rarely reaches technological complexity. If that is true, then intelligent civilizations like ours may still be rare even in a biologically rich universe. That thought is strangely humbling. It suggests the universe may be alive in ways largely invisible to us. Quiet life, hidden life, dark ocean life, worlds where biology thrives beneath ice untouched by starlight. And then comes the philosophical shift. For centuries, humans often imagined life as something tied to surface worlds, blue skies, sunlight, oceans, weather continents. Earth shaped our imagination. But Enceladus challenges that bias completely. It suggests life may not prefer surfaces at all. That is a radical thought. Surfaces are violent places. Radiation impacts climate instability. Stellar flares, atmospheric loss. Surface environments can be dangerous over geological time. Beneath thick ice, however, oceans gain protection. Ice shields against radiation. Internal heat stabilizes chemistry. Subsurface oceans can remain insulated for billions of years. Paradoxically, some of the safest habitats in the universe may be hidden, not under blue skies, under ice. That idea transforms the map of habitability. We once searched primarily for Earth-like planets. Now we increasingly recognize that some of the best habitats may look nothing like Earth from the outside. Frozen shells, dark interiors, invisible oceans. Worlds that appear dead, yet may be alive within. That realization changes not only where we search, it changes how we think, because perhaps life is not easy to see from a distance. Perhaps the universe has always been more alive than it appears. And perhaps Enceladus is teaching us that our biggest mistake was assuming visible activity equals habitability. Sometimes the most important worlds hide everything that matters. Beneath the surface, that idea feels strangely human. We too often misunderstand what lies beneath appearances. The most transformative truths are not always obvious. Sometimes they are buried, waiting for patience, curiosity, and better tools. That is the deeper meaning of Enceladus. When William Herschel first observed this tiny moon in 1789, he could not have imagined what it truly was. To him, it was a faint point of light orbiting Saturn. Nothing more. 2 centuries later, humanity learned that this tiny point of light may contain a global ocean hydrothermal activity complex chemistry, and perhaps the conditions necessary for life. A world once dismissed as insignificant became one of the greatest scientific mysteries of our age. And that may be the most powerful lesson of all. The universe does not always reveal its greatest secrets through its largest objects. Sometimes the most important discoveries come from places we almost ignored. A tiny moon, a frozen shell, a hidden ocean, a question older than civilization. And so, after all the missions, all the data, all the chemistry, all the equations, we arrive back at the same profound uncertainty. We still do not know whether anything lives beneath the ice of Enceladus. Not yet. But for the first time in history, we know where to look. That alone is extraordinary. Somewhere beneath kilometers of frozen crust in a dark ocean warmed by gravitational fire. Chemistry continues. Water touches rock. Hydrogen rises. Minerals circulate. Energy flows. And perhaps right now, something microscopic is metabolizing in that darkness, not waiting to be created, only waiting to be discovered. Because maybe the greatest revelation of Enceladus is not that life might exist there. Maybe it is this: the universe may not be asking whether life exists. It may already be full of life, and we have only just begun to notice. So, the next time you look up at the night sky, remember this. Far beyond Earth, beyond the asteroid belt, beyond the giant rings of Saturn, a small frozen moon continues to spray pieces of its hidden ocean into space. Every plume is a message. Every ice grain is evidence. Every eruption asks the same question, a question that may define the future of science. If life can emerge in the dark beneath alien ice, how many living oceans are still waiting for us in the cosmic night?